What we will start now is what is called the finite difference time domain method, right. Many of you may have heard this word in the past, right. It is in fact one of the most popular methods in computational electromagnetics. Right. So, this is what we are going to roughly do. We are going to motivate and give some history about this problem, and we will deal with a 2D formulation and then look at various aspects, numerical analysis of this method. Okay. So, let us start with the introduction. So, as before, we would like to start with a little bit of sort of context and history. So, FDTD, that is the short form that we will be using throughout, finite difference time domain. Okay. So, we will see why we call it finite difference time domain. So, few very general points first. So, it is the simplest, okay, and also the most what can you say, most widely used. Okay. Not just in the electromagnetics community, but even in the optics community, this method is used extensively. Okay. So, if you ask when was the original formulation, right. So, there was a very landmark paper by the person called Yi in 1966, which laid the foundation. And in fact, when you look at this method and the paper as formulated by E, you would think, oh, I could have done this. You know, it's really that simple. In fact, the central idea of FDTD can be told to you in this one slide, and that is it. Okay. The rest of it are all just details. So, before we come to that, what we have seen so far before we came to FDTD was we looked at integral equation methods, and then we looked at FEM methods. So, you can ask one question now, why do we need yet another method? Okay. In integral equation methods and finite element methods, what was how did we deal with time? Did we deal with time at all? Right. So, in these methods, what did we assume? E to the j omega t, right. So, you can say harmonic form of the field was assumed. If I wanted to have some time dependence in the problem, what would I need to do? Supposing my source, let us say my radar source is not single frequency, but it is some ultra wideband thing, and I wanted to use IEM or FEM, then what would I do? Solve for each frequency and then use Fourier transforms to get the answer, right. Now, if my system, electromagnetic system actually is very wideband, lots and lots of frequencies are there, then you can see that this both IEM and FEM will become very tedious, right, because not just you have to do computational EM, you also have to do then Fourier transforms and all, and over very large data sets. So, that becomes tedious. So, instead this FDTD is directly formulated in the time domain. Okay. So, very useful for time domain formulations. Can you think of some examples where you might where the problem is naturally posed in the time domain? If I want to see how a wave propagates, so if so a wave propagating like e to the j omega t from a pulse, right. So, like you want to, a pulse is traveling and you want to see how it goes in, right. So, that can be one thing, right. So, wave propagation, but we want pulsed form, right, because continuous wave form is already e to the j omega t, right. So, pulse form. So, the like a radar pulse has a finite time duration, right. So, it cannot actually be approximated as e to the j omega t. So, that is one case. So, you want to see in real time how is the wave propagating. Any other situation? Transient phenomena, yes, transient phenomena is very important. Example? What is the most transient electromagnetic phenomena that you can think of? Natural phenomena. Huh? Switching, yeah, switches, yeah, okay. So that's a more down to earth example. Switching, right? There's a circuit, there's some switching happening. So that's your EMI, EMC as they call it, electromagnetic interference problems. There is some gate that is operating at some switching rate, and because of the switching, it is producing some electromagnetic waves. That was something naturally in the time domain. Natural phenomena, lightning, right? Very sudden burst of electromagnetic energy. In terms of frequency content, it will be all frequencies, but in time domain, it's localized to a very small point in time. So that might be one example where time domain formulation is better, right? So you can say switching in general. Okay, so as it turns out, the number of applications where time domain is the more natural domain is actually more than frequency domain. So that's why this FDTD is more widely used than the other two. Okay, it's also a little bit of a brute force method, as we will see. Okay, so let's see what is the basic idea. So unlike the integral equation methods, the FDTD is based on the partial differential equation form of Maxwell's equations. Okay, so it's based on differential form, not integral form. So let's make the assumption. We'll start with a very simple assumption of a medium, and as we go in subsequent modules, we'll generalize it. Okay. So I'm going to assume a linear medium. Linear medium means, well, that is what you said was about isotropic. So let's say isotropic medium. Epsilon is equal to, is a scalar, right? The permittivity and permeability are scalars. Okay, let's make one further assumption that it is a non-dispersive media. What is non-dispersive? What does the word non-dispersive tell you? The permeability or permittivity rather does not depend on frequency. If you take this feature away, you cannot have a rainbow, right? So we are making some very strong assumptions, but we'll relax these as we go. We want to just give the central idea first, then we can generalize it. Okay. So over here, under these assumptions, I can write down that my displacement field can be written as just a scalar times electric field. Okay, and B also can be written as mu h. Okay. In particular, this assumption we will change later, but it takes a lot of work. Now, with this having been said, what happens to our Maxwell's equations? I mean, we have seen all of this before, right? So, the first equation will become curl of, let's write it in this form first, let's write it del by del T of D. Okay. So, that becomes, that is simply curl of H minus J, right? And that simply becomes epsilon, electric field. Okay, that's your first equation, and then the second equation is curl of E, and that becomes okay. Isotropic means, yeah, good question. So what does isotropic mathematically means? Isotropic means that epsilon, so physically what does it mean? That no matter which direction you go, the wave experiences the same medium. Okay, that means epsilon is a scalar number. Okay, but if it is anisotropic, then the wave experiences a different property, let's say different propagation speed in this direction, that direction. So epsilon over there becomes a tensor. That
so epsilon, how is linear different?
How is linear different? Okay, So linear means that epsilon does not depend on the strength of the field itself. That would make it a non-linear medium. For example, does the refractive index depend on the intensity of light? In general, no, right? If I take a glass, it has a refractive index no matter what beam I send through it. But in optics particularly, there are non-linearities where the refractive index begins to depend on higher powers of electric field. Then you call that a non-linear medium. Okay. So all of what I said, so linear and isotropic means I can write epsilon as a number.
I thought isotropic meant like epsilon will be some x or epsilon of xy,
Huh?
so that it varies with space.
That is heterogeneous or homogeneous.
Oh.
If epsilon becomes a function of space, then we call it a heterogeneous medium. Okay, but I can have a homogeneous medium that is anisotropic.
Oh.
And the most common example, the most common use of this is in optics, what are called birefringent media. They have different propagation constants in different directions, even though it's a bulk medium. And that comes from atomic structure of the material. There's a asymmetry in the atomic structure.
Maybe like the displacement, d in one direction affects d in
Yes, that is also possible. Yes. So what he's saying is that the displacement field can depend on electric field in different directions. So that is taken into account by making epsilon to be a tensor. Okay. So those are all the sort of complications. So one more thing I should add over here will be time invariant. Why should I add that? So is that epsilon can come out of the d by dt. Right. So we are assuming that the medium is static. So when we begin to list out the assumptions, you can see that there are so many over here, right. All right. So let's actually write this equation on the right hand side. Make some space over here. So we had del B by del T is equal to minus curl of E. So far I have only told you about the differential form, and now what is the central idea that you use in finite difference time domain? It's basically built on Taylor's theorem. Okay. So Taylor's theorem will tell us that f of say z naught plus delta z by 2. Okay. So let's take this. We all know this, f of z naught is the first term, next term is delta z by 2 f prime, right, and higher order terms. Okay. What is the in the Maxwell's equations that we have seen, what is the order of derivatives that are coming in space and time? First order, right. So we will just retain our discussion to first order for now, and by symmetry this will become minus delta z by 2 right. So if I wanted an approximation for the first derivative using Taylor's theorem, what can I say? What will Taylor's theorem, can Taylor's theorem be used to give me an approximation for first derivative of a function? Yes, what should I do? Subtract these two equations. If I subtract these two equations, what happens? F of z naught cancels off, right, and then I am left with delta z by 2 is common and it is there 2 times, right. So that becomes delta z on the right hand side, delta z times f prime, and the left hand side will become f of z naught plus delta z by 2 minus f of z naught minus delta z by 2, right. So this implies that f prime, now I will just write it as f prime of z naught, but you should know that this means f prime of z evaluated at z equal to z naught, right. It is understood by now. So this is your f of z naught plus delta z by 2 okay. What is the error term over here? There is an error term over here which I am ignoring when I subtract. What order will it be? Square. It won't be cube because there's a I'm dividing everywhere by a delta z, right? Subtract these two equations and then divide by delta z. So I'm left with a because if you see the second term on both of these is going to have a delta z squared, which will get cancelled off. The next term will be delta z cube, and when I divide by delta z, I'm left with the error term of order delta z square. Okay. So this is these sort of the central idea of finite difference time domain. Replace derivatives by differences. What kind of differences are they? Finite differences. So differences between finite values in space. So this z can be space, z can be time. It's up to me, right? So what this is, I mean, there's a technical name given to this kind of a difference. So it's centered, okay, 2-point finite difference. Okay. So this is the basic idea. So Maxwell's equations, Taylor's theorem, this is all that you need to develop the entire FDTD method. There are, I mean, the other concepts here will deal with how to deal with, you know, anisotropic media and heterogeneous media and all of that, right? But those are all details. The main conceptual work is going to come from this part over here. So notice one thing over here. Supposing you solve a problem with a certain discretization. If I half the discretization, okay, what happens to the error? If I have a problem, I have solved it using this, details we'll see, but I have solved it using replacing these finite differences. And now I say I want a more accurate solution. So when I reduce, make delta z, make it delta z by 2. What happens to my error? Increases, decreases? Decreases by a factor of 4, right? So that's the reason why you use this centered 2-point difference. Because if I just look at the first equation over here, if you look at the first equation, that alone gives you an approximation for the first order derivative, right? I can write from here the first order derivative in terms of f of z naught plus delta z by 2 minus f of z naught. I can do that. But there the what happens to the error term? Order delta z, right? Do you follow? Okay, so let's see. So let's maybe we'll write it over here. So I can also write f prime of z naught approximately as, just using the first equation alone. So f of z naught plus delta z by 2 minus f of z naught. Okay, let's, and what is the next? So we'll keep this delta z by 2 here. Okay, so I'm just rearranging the term. And what are the other terms over here? Order of delta z square. Now I can divide this expression on both sides by? No, I have just rewritten this first equation. The first equation had second order terms and so on, which I am ignoring. So when I divide this equation by delta z by 2, what happens? The order becomes, I mean the error becomes of order delta z, right? So so the approximation now, if I make my if I reduce my discretization by a factor of 2, my error also reduces by a factor of 2. So the other scheme which I derived over here, this centered 2-point difference is better because halving the discretization makes the error go down by a factor of 4, right? So this, the error term is what I am talking about. How does the error behave as a function of discretization?
So the error is the order of delta z squared.
Yes, the error is of order delta z squared in a centered difference. What I have written over here is called a one-sided difference. Okay. Divide by delta z by 2. See, I am trying to approximate f prime z naught.
Yeah. So okay, right.
No, start with this equation. Taylor's theorem, plain and simple. I am just rewriting here, bringing the f prime z naught term on one side, everything else on the other side. I have not done anything so far.
Okay.
And now I have divided by delta z. Okay. So, these inside the computational domain, everywhere I use a centered 2-point difference, but I am forced to use these one-sided differences sometimes at the end of the computational domain, because there is no point outside. So, there I may be forced to use a one-sided difference. Okay. So, these are some of the compromises or tricks you can use given some differential equation. Also, you notice that there is nothing very sacred about Maxwell's equations here. Given any system of partial differential equations, I can use this technique, right? Nothing special about Maxwell's equations. Right? So, this is the basic idea. Maxwell's equations, finite differences.
So one more thing.
Yeah.
You are going to replace E with all these, basically E of z naught plus
E, H, wherever I see a derivative in space or time, I am going to replace it by a finite difference. That is the philosophy.